right, let's get started. Welcome to this session, Materialized Pre-Aggregations for Exploratory Analytics Queries. I know the title is a mouthful, but I promise you by the end of this session, we will have gone through the sentence word by word. A bit about myself. My name is Thomas Rücksties. I'm a staff engineer at MongoDB. I've been with MongoDB for close to 10 years now. And just how our products have evolved and our branding and logo has changed over time, so has my role. More recently, I was the lead engineer for MongoDB Compass and later Atlas Charts, our data visualization tool. And last year, I joined MongoDB Labs. It's our research and innovation team. And the projects I'm involved in are usually around analytics and machine learning. On the left, you see me making pizza. And you will soon find out what pizza making has to do with analytics. Data is said to be the new currency. So it's no surprise that many businesses want to use their operational data also for analytics queries. But as Sahir mentioned in the keynote this morning, analytics queries are very different to your typical application workloads. They require different techniques, different methods to make them performant. So in this talk, I'm going to give you a few examples of how you can do that, and then focus on one in particular that works well for data exploration. And I want to start with a visual overview why these types of workloads are so different. You have your transactional or your OLTP workloads, and they usually access individual rows or documents. They can be read or write workloads, and often they want the entire document. And that is in contrast to analytical queries. They often access the entire data set or large portions of the data if you have any filters, but they're mainly just concerned with a couple of columns. Yeah, and it's that difference why it is so crucial that for your transactional workloads, for your application workloads, you need indexes to make them work well and performant, but they are less effective for analytics queries. And there are other things we can do to make them faster. And of course, if we talk about analytics, there are also different types of analytics. Yeah, I've got 3 different categories here. There are different ways of classifying them, but you might have your real-time use case, where you want to do decision-making in real time, for example, fraud detection. Imagine someone swiping a credit card, and you have to decide whether to accept or to decline at this time the swipe happens. So here, the latency expectations are often in the milliseconds. And then on the other side of the spectrum, you have reporting. Here, the queries are often known in advance. Say you want to create a report and email it out at the end of the week, or you populate a dashboard to see your user growth every day. So these queries often run on a schedule, and it's totally fine if they take minutes or hours. Yeah, they can run overnight, and then when you come in the office next day, you can see the results. And then there's exploratory analytics as well. Exploratory analytics, you usually have a human involved. They run ad hoc queries, often through BI tools like charts or Tableau or something like that. And here the latency is somewhere in the middle of the spectrum. Yeah, they can take seconds or minutes, but we are impatient, so humans often don't like to wait longer than that. So what are some ways to accelerate OLAP queries then? Well, at query time, what's very effective is to have the right layout, the right storage for your data. So you could imagine a columnar storage or columnar indexes like we announced this morning in the keynote. They work well for ad hoc queries as well. The problem with this is the integration cost is usually very high. In fact, you often rely on the database vendor to build a different storage format or different type of indexes. After query happens, you can do result caching. It's very easy to do. A lot of applications do that at different layers of the stack. But that relies on if you're actually interested in the same result again. Yeah? If you never want to see the same result, then caching won't help you here either. And it doesn't work well with fast-changing data because your data gets stale, your caches, and you have to recompute them. And there are also some things you can do before the query actually happened. And that gets us into the realm of pre-aggregation or pre-computation with materialized views. Here, potentially, you have the biggest upside. If you could perfectly predict what queries are being issued ahead of time, you can front run them and just serve the result when the query comes in. But that's obviously not always possible. It requires a lot of knowledge about your application use cases and it doesn't work well with ad hoc queries. If you don't know the query in advance, you can't run it in advance. So in this talk, I'm going to focus on that last category, and I'll show you how you can work around that ad hoc problem, and how you can make that work even for queries that you don't know in advance. And I've already mentioned materialized views, so I just want to quickly show you how you can use them in MongoDB. In fact, they have been a feature in MongoDB for a long time. A materialized view is just a fancy name for storing a result of an aggregation in a collection. Here I have an aggregation pipeline. If you're not familiar with the aggregation framework, these pipelines consist of different stages. Here I have 4 stages: a match, a group, a sort, and a limit. Each stage processes the data in some way and then passes the result on to the next stage. So in this case, I'm filtering on the developer's job role. Then I group all these developers into their home countries and count how many I have for each country. Next, I sort this list in descending order, and then I just take the top 10. So if I wanted to visualize the result of this query with a chart, it could look something like this. So this is an individual query. If I want to persist the result in a materialized view, all I have to do is add another stage, $out. There's also $merge if you want to update a view, and give it a name, and then it stores the result back into that collection. And then it can be accessed, for example, for this chart. It could be rendered many times without having to execute this pipeline over and over again. Materialized views in MongoDB refresh on demand, which means you can either issue the aggregation pipeline again manually, or you can also use Atlas triggers. Yeah, triggers let you set up a schedule where this pipeline runs, say, every hour or every day. You can set the times exactly. It's like a cron job. You can also react to database changes, yeah, so database triggers. So you can run these pipelines when the data has changed. So let's see how we're doing with our title. I mentioned the difference between OLTP queries and analytics queries. We talked about pre-aggregation as one of the forms of accelerating these queries. And I mentioned materialized views. So if it wasn't for that word exploratory, we could be done now and could all go get a coffee. But unfortunately, exploratory queries by definition are ad hoc, and we don't know them in advance. But yeah, I'm here to tell you that you can still do pre-aggregation for these types of queries. And in order to show you how that works, I want to give a little analogy. So here am I, again, making pizza. If I bake pizza, I like to do everything from scratch, including the base. Yeah, I take the raw ingredients, make a dough, let it sit for an hour or so. Real Italians would probably tell you that that's not nearly long enough and has to proof for 24 hours. But if I do pizza for myself at home, that's fine. And then I roll it out, put the toppings on, put it in the oven. All in all, that takes maybe an hour and a half. That's not how restaurants make pizza. Yeah, they would have a lot of unhappy customers if you order pizza and it takes an hour and a half. So what do restaurants do? Well, they actually make the dough ahead of time. I don't know exactly how long it takes. There's probably some process. But it doesn't really matter because the bottleneck is the 24-hour proofing. Yeah, they let the dough rest overnight. But then they can make a pizza in just a few minutes. Yeah, when you order it, they just roll out these doughs. And not just a single pizza, they can make any pizza with these doughs because the base is always the same. So in a way, bringing this back to databases, you can call this first step pre-computation and the second step ad hoc. And that's exactly what we want to do with our aggregation pipelines. We need to find the bottleneck and try to do as much of the work that we can ahead of time, but without losing the flexibility of answering a large class of different queries. So let's talk about exploratory analytics a little bit. I already mentioned exploratory analytics means we have a human involved, and humans like to look at data in a visual form. And the reason for that is simple. Yeah, our human eyes are really good at detecting patterns visually and finding outliers. And they're actually quite terrible looking at data in text form. So here I have just a selection of charts that Atlas Charts can create. They all look very unique and distinct from another, but they all have one thing in common. they all have a $group stage in the aggregation pipeline that creates the chart data. So here I have this pipeline again with the group stage highlighted. And the thing about this group stage is that it acts as a kind of dimensionality reduction. Yeah, we're going from potentially millions of documents in the original collection down to often only hundreds of documents. And each document in the result after the group stage actually corresponds with a visual element in your chart, like a bar in a bar chart. So you really only have a handful, often even only 10 or so. The other thing about this group stage is that it's a blocking stage, which means it has to process all the data first before it can pass anything to the next stage. And that's a slow process, and that is typically the bottleneck in these pipelines. So this group stage is the perfect candidate for our pizza dough. Yeah, we have to try to do this ahead of time, but we can't hard code these fields. We have to make it in a way that it's flexible, that it can answer different queries. So how do we do that? Well, I'll give you two fun facts about $group. The first one is that we can compute multiple fields in a single pass over the data set. And the second is that for these typical aggregate functions like sums and counts and averages, these buckets that come out of a group stage, they can be recombined again afterwards. So we can reverse the process. Let me show you what that looks like. So here I have a single group stage on one dimension and one measure. So the dimensions are the fields that we group by. They go in the _ID key, here home country. And the measures are typically numeric. That's what we aggregate over. And they also need an aggregate function, in this case, $average. And visually speaking, what I get is a bucket for each distinct value in my dimension, yeah, for each country, indicated with these green diamonds. And each bucket contains one measure, one scalar value, the result of the aggregate function. Now I said you can do this over multiple fields. So let's see what happens if I add multiple measures. So you see here I added average age. I also have min age and total experience. I now get multiple scalar values for each of these buckets. I can also add multiple dimensions. And that's what that looks like. And now I get one bucket for each unique combination of values of my dimension fields. And I can keep doing that. Here I've added another dimension, and I end up with this three-dimensional cube. And if that starts to look familiar to you, maybe you have heard of or even worked with OLAP Cubes before. Because this idea isn't new. Yeah, OLAP Cubes have been around for, I think, 20 years or so. And they are also more known in the relational world, but the core idea is universal. Yeah, you can implement this with the aggregation framework. So I've added these dimensions, I've added these measures. That was our fun fact number one. I can do that over multiple fields. And I can also combine these cubes again. So what does that look like? This works. Yeah, I can add up cubes again to get the result because these operations, they are associative and commutative. This means the order doesn't matter, and I can recombine already calculated results. And for counts and sums, that's quite simple. I just add up the intermediate counts and sums. For minimums and maximum, I take the minimum of the minimums, the maximum of the maximums. And then for average and standard deviation and so on, it also works. The formulas get a little bit more complex, but you can do that. So I can combine cubes. And if I combine all the cubes along an entire dimension, yeah, like shown here along this yellow arrow, what I effectively do is I project out that entire dimension, and I end up with the state as if I had never added that dimension before in the group stage. So that means this operation is reversible. Now that's interesting. So what that means is I can take my raw data, I can compute these high dimensional cubes and on a lot of different dimensions and measures that I might be interested in, and that's my intermediate state. Yeah, that will take a bit of time, but I can store that, and then I can query this cube. And I can project out dimensions to answer any individual query. And most data visualizations, they live up here in that lower dimensional space. Yeah, We can only process 3-dimensional information with our eyes, but charts are even often only 2-dimensional or 1-dimensional. So I can calculate these things from these cubes. Okay, so that was a lot of theory, but I wanted to explain why this principle works. And now I'm going to show you concretely on a data set what that looks like in action. So here I have the DMV dataset. That's vehicle registrations in the US. It's 11.6 million documents in this particular case. I chose that dataset because it's fairly large, and we can actually see the performance differences quite nicely. So in this case, I'm going to build a cube on these green dimensions. I pick state, color, the model year, fuel type, and a Boolean flag called suspension indicator, whether the license was suspended or not. And I use the weight of the vehicles as a measure. So let's take a look at the aggregation pipeline, what that looks like. So you see here at the top, I have all these dimensions that I'm interested in. And then down here, I have 4 measures. First, I use just the document count that's independent of any field. And then I'm interested in the minimum, the maximum, and the sum of this weight field, just as an example. So that's how I define my cube. And then I write that out to a materialized view. I'll show you what that looks like in action. So this is a recording where I do that in the Mongo shell. Here I run this aggregation pipeline. I've actually cut out about 30 seconds in the middle. We'll see that in a second. The whole aggregation in this case takes about 45 seconds or so. And once that's finished, I can inspect this cube collection. Yeah, first, I can count how many results are in there. And you see I've reduced this data from 11 million down to 37,000 only. And that's where this performance gain comes from, because if I query this cube now, I only have to process many fewer documents than before. Here's an example of what that looks like. You see the dimensions, they're nested here under this underscore ID key. And then down here we have the results for the measures for this one particular cube that's described as this document. Okay, now I have this cube, and now I can actually query that. Here, in this first example, let's say I'm only interested in the total document count. You could use the $count stage for this. $count is just a syntactic sugar under the hood. It uses a group stage with a constant dimension. So basically just one single bucket. We're throwing every document in that bucket, and we just count 1 for each document. This is the original pipeline that I would send against my original collection. Now, if I want to query this cube, I have to make a couple of tweaks. First, I need to query the actual cube collection instead of the raw data. And because we've already added up some of the documents, I have to sum up these intermediate counts instead of 1. And I'll show you what that looks like again in the shell. First, I run it against the source collection. You may also notice there's a little underscore in that aggregate function. That's just a wrapper that I wrote that also gives us the timings, but otherwise it's just a regular aggregate. So you see this took 7.4 seconds to run on this data set. And now we're querying the cube with that slightly modified pipeline. And it takes 48 milliseconds. Yeah, that's a performance gain of 150, roughly. So here's a second example, a bit more complex. Now I'm interested in the heaviest vehicle registration for each year. Yeah, the maximum of that weight field. Then I sort that in a descending order, and then I just want to see the top 3 years with the heaviest vehicles. This is the original pipeline. Again, querying the cube, I need to make some tweaks. So you saw the dimensions are actually nested under the underscore ID field. That's just how the group syntax works. So we have to factor that in. And then we named the maximum of the weight with the underscore max. So we have to calculate the maximum of the maximums. And I can run that as well in the shell. I think I sped up that video a little bit. It's 2 times or so. But we get the timings. If I run that against the original source collection, it takes 18 seconds. And then if I run that against the cube, it's 89 milliseconds. So orders of magnitude faster. And in fact, it's actually independent of the original data set. Yeah, it's the number of documents in the cube depend on how many unique values of dimensions we get. Like everything, this approach does have some limitations. I'm giving you the two main ones here. The first one I call the curse of dimensionality. So the issue with adding more and more dimensions, yeah, you might be tempted to say, okay, let's take all the fields we have, is that the results number grows exponentially. Yeah, you can imagine if you add more dimensions for every combination of values, we have to create one of these cubes. And eventually, if you approach the original number of documents, the advantage is lost, and it may not be much faster than going to the source directly. So that's one issue. Just keep that in mind. Don't add dimensions that you don't need. And the other one is filters before the group stage. Yeah, this cube was calculated without any filters. If you then add filters before the group stage, that messes up the aggregates, and they won't be correct. It's not as bad as it sounds. If these filters are on dimension fields, then it does work. You can then actually swap the match stage and the group stage, and everything will work fine. But if they are on different fields, on your measures or even on unrelated fields, then that may not work. And you may have to calculate a separate cube for your filters. So that's just two things to keep in mind here. And I'll leave you with some key takeaways. So you can use materialized views to speed up these analytics queries. You can pre-aggregate group queries along these fields of interest, the dimensions and the measures that you're interested in. And that is basically the core idea of the OLAP Cubes implemented in the aggregation framework. I've made a little GitHub repository, so you can go to GitHub on MongoDB labs/cubes. There's some code that can write these pipelines. It also helps you with rewriting the pipeline, so you don't have to do that manually. That can all be automated, and you can replay the examples that I've given you today. Thanks very much. And I think we do have a bit of time if there are any questions. Yeah. Yeah. Okay, so the question was like, what is the key aspect to maybe use this method to pre-calculate the cube versus running the query directly against the data? So I think you would run into performance issues, and that is a good indicator that you may want to pre-aggregate your data. If your visualizations take minutes or longer every time you run that, that's also quite a load on your database. You may want to use a method like this.
But maybe it's not if you run it multiple times a day, or like you are within a project or something like that?
Yeah, if your queries only take a few seconds and you're okay with that delay, then that's fine. Then you wouldn't need to use that method. But as your data size grows, say you store all your historical data, even say in S3 or something, your data set will grow unbounded. And at some point, these queries will just not be performant anymore. Yeah. So you could pre-aggregate them overnight, and then you have this cube, it's fresh for that day, and then you can run very fast queries against the cube.
Question is, what are the best practices to manage such views? If let's say I have a data set of 1 terabyte of data, right? And then I create these views, and now my data changes, but not all of it. Mm-hmm. What are the best practices to maintain those? You drop the collection and then create a new one, or there are ways to modify it?
Yeah, so it really depends what your data exactly looks like. If you have time series data, for example, then that's usually just append only. And then you probably wouldn't want to delete all your pre-aggregated data because you only add more cubes. So you could actually use the $merge operator and just update the view with the latest data. But if you have updates and deletes as well in your collection and you modify previous data, then you would have to recalculate the entire cube to bring it back in sync with your data.
Yeah, you mentioned refresh is on demand, right? Mm-hmm. Can we schedule or something like that?
Yeah, I did mention that. So you can use Atlas triggers. Where was that? Sorry, here. So in the Atlas UI, you find triggers under data services. And these triggers, you can set up aggregation pipelines. And those could be also these. Sorry? Yeah, you can put some logic in there. You can actually deploy functions there as well. They check for certain conditions. And you can either trigger on a schedule, or you can trigger on data changes. Yeah.
So some queries might be slower than others. So is it possible to optimize the cube or this aggregation so that it works faster on those slow queries and you remove potential bottlenecks?
So if you know that some queries will just be fast, for example, they don't use a group stage or something, and you just query the data set differently, you can, of course, query the source collection as well. You don't have to send everything to that cube collection. So you can control, you send the slow queries to the cube, and you send the regular queries, the faster ones, directly to the collection if you want.
Will this work seamlessly if we have multiple nested docs inside the collection?
If you have nested docs, it really depends what you want to see in that data. You would have to write that group stage in a way that accesses the fields that you want. Yeah? If you want to group on certain fields that are nested, of course that works. You can express that with the aggregation framework with the dot notation. But yeah, there may be a bit of planning the schema, how exactly that cube collection looks like. Yeah.
Hi.
Oh, yeah?
So what kind of design pattern would you recommend where the aggregations are not reverse computable? For an example, the weighted average, where you cannot just take out one dimension and the aggregation becomes kind of invalidated. So what kind of structure would you recommend when I want to do something of that kind of aggregations?
Sorry, I didn't hear the first part.
So when you have a weighted average, not the regular average, in that case, the dimensions that you use is not collapsible or reverse computable.
Yeah.
And the cubes are not I cannot have 3 dimensions and then remove 1 dimension and recompute the weighted average, or the deviations or something. So what kind of pre-aggregations can I do? What design pattern would you recommend for those kind of stuff?
So you mean if you have missing values for certain dimensions, or
maybe let's say weighted average or the deviations, right? That depends on exactly the same number of dimensions. So we talked about we can add more dimensions, and then if you remove, that's still reverse computable or something. But there are certain aggregations that are not. So what design patterns would you recommend for that?
I'm not quite sure. I probably have to think about that a bit more. So you're saying you don't know the dimensions ahead of time?
Yeah, sometimes, yeah.
Okay, that's tricky then. I mean, one thing you can do is you can, of course, create multiple cubes with different dimensions. You don't have to put everything in a single cube. That's also a good method if you have a lot of dimensions, like I mentioned, this curse of dimensionality. If you just have too many dimensions, but you're not always querying all of them in the same, say you have 2 types of query patterns. One queries dimension ABC and the other one B, C, and E or something like that. You can create 2 separate cubes, and then you can query these individually.
I see. Yeah, got it. Thank you.
Yeah. Yeah.
I've got a loud voice. I have a question. It's more like a way of thinking. So when I hear like, okay, you've got a 6 million collection DMV, right?
Yeah.
Every time you can do an insertion, certainly I can trigger recomputation. Let's just say that the throughput's much higher. Now let's start something new. So I can trigger it every 10 seconds. Conceptually, how would you go about thinking about
So if you have a heavy write load to your collection, and yeah, you probably wouldn't want to trigger a recomputation of your cube with every single insert. Yeah. So you have to weigh off how fresh does your data need to be. Do you really need second freshness or minute freshness, or are you okay with an hour-old data for your visualizations, for example? And then, depending on that, trigger the refresh of the cube. And the other thing is if you have, for example, time series data, you don't have to recompute the entire cube. You can actually just append new cubes only of the data that just arrived. So you can do that in an incremental fashion. And that might be much faster then. Yeah, that's right. Okay. More questions? Yeah. Some of the yeah.
Oh, sorry.
I mean, you can only access fields that are in the cube. So you have to, at the time of creation. The cube is basically just a regular collection. So you can do any kind of thing that you can do with other collections as well. You could have a pipeline that queries the cube and then does a lookup on a result from a different collection. So it's quite flexible in that sense. Yeah, it's like materialized views are really just collections that you can do, and you could do that. Yeah.
These are writing to production database, is that right? In the examples, is there a way you can do it on an analytics node without impacting production write performance?
So you can query the analytics node if it contains the collection. Yeah. But you have to write to the same cluster in order to get it there. What you could also do, so we mentioned this morning in the keynote, federated data lake. So you could actually write out that cube to S3 and then query it through data federation as well.
Okay. Are there more common examples of metrics? Oh, sorry, measurements. You mentioned some average. Are there any other common you can quote? You can mention?
So the most common ones, they all work fine. So that's counts, sum, average, min, max, standard deviation works, variance works. The issue is they have to be associative and commutative, these operators. If you have something that's not reversible, like for example add to set or something where you can't actually do that and then combine the cubes again, that won't work. So there are some limitations what you can use, but those are the most common ones. So I can tell you, I was the lead of Atlas Charts before, and we have some metrics of what types of charts users build. And I think it was 92% of charts use only these 5 aggregate functions. So they're really the most common ones. Yeah.
Before next question, so we already ran out of time.
Okay.
So if you want to get lunch, feel free to go get lunch. If you want to stay, you can stay. I mean,
I'll be around as well if you have any more questions.
Yeah, we can answer a few questions.
Yeah, thank you.
All right. My last question was,
yeah.
You said there are 2 downsides, 2 pitfalls. The second one was don't use a match before a group. Is that correct?
Yeah, so when you calculate that cube, you would do that without any filters normally. And then if you have filters in front of, or match stage in front of the group stage, then that doesn't, like these cubes, these pre-calculated cubes, that doesn't work anymore, because now you only want some of the results, but you've already added them up, all of them, in one cube.
But if you're wanting to aggregate and cube data for like a particular subset of your data, then that's fine, right?
That's yeah. So if you actually, I can show you something afterwards. If you filter on dimensions, that's fine. That can work. You just have to put the match after the group stage. But that works because these cubes, they're all discrete along the dimensions. If you want to filter on measures, there are some tricks you can do. You could, for example, add the measure as another dimension as well in bind form. Yeah, so you go 0 to 10 is one, 10 to 20, and so on. And then you can make it work. It's just getting a bit more tricky to implement all of that.